Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this 25th lecture of the course entitled Advanced Transition Metal Organometallic Chemistry. In the last lecture, we have been talking about the reactivity of transition metal arene complexes. We have looked into the different reactivity patterns of these bis arene transition metal complexes and compared them to that of their cyclopentadienyl counterparts. And what we had seen that these bis arene transition metal complexes are more air and moisture sensitive as compared to the metallocene counterparts. Furthermore, we had also seen in our last lecture that these transition metal bis arene complexes are more vulnerable to oxidation. We had also observed that these transition metal bis arene complexes are kind of kinetically inert towards ligand exchange if it were simple bis benzene type complexes. However, for condensed arene complexes, the ligand exchange reactions are quite favored, and we had observed the formation of mixed benzene naphthalene dinuclear complex of chromium through this taking advantage of this ligand exchange reaction of condensed bis arene transition metal complexes. Also, another sharp difference between bis arene transition metal complexes, particularly with respect to the bis cyclopentadienyl transition arene complexes, is the fact that these bis arene transition metal complexes does not undergo electrophilic aromatic substitution reaction similar to the ones that we had observed for cyclopentadienyl transition metal complexes. In fact, what we observed in case of bis arene transition metal complexes is that the electrophile instead of undergoing electrophilic substitution reaction at the aryl ring ends up oxidizing the central metal atom and does not participate in the electrophilic substitution reaction. Continuing further on this the reactivity pattern of bis arene transition metal complexes, we are going to take up another interesting reaction on this topic, and this is called the metallation reaction. What in contrast to what we had observed for cyclopentadienyl transition metal complexes, particularly with that of ferrocene, what we had seen that in presence of lithium reagents, multiple lithiation was a problem, and there was sort of not a simple strategy to get monolithiated or selectively monolithiated or dilithiated pattern for this kind of cyclopentadienyl transition metal complexes. Unlike that, in case of transition metal bis arene complexes, selective dilithiation can be affected by performing the reaction in presence of TMEDA as is shown over here. gives this dilithiated product with lithiation occurring in each of the two rings. Now, it must be noted that this pi bonded benzene is methylated more readily than free benzene. Free benzene. The another interesting thing is that this dilithiated product with lithiation in each of the ring was indeed observed even for metallocenes, again in presence of TMEDA. So, this method of obtaining dilithiation is not only same, not only is similar to what is observed for bis-arene transition metal complexes, but also was observed for bis-cyclopentadienyl transition metal complexes. Now, this is a useful intermediate which can be converted to many other interesting reagents, leading to substitution on the ring, as is shown over here. So, reactions with MESS Me minus LIS Me gives the substitution of SME on the ring or reactions of Me2 GeCl2. Now, this is a method whereby ANSA system with bridging dimethyl zirconium can be created of the formula somewhat like this. M equal to vanadium radical, and third one is PPH2 PCl, and then reaction with molybdenum hexacarbonyl, giving this beautiful dinuclear complex of bis-benzene vanadium radical with PPH2 molybdenum CO4. So, what we had seen that though electrophilic aromatic substitution was kind of a hindrance or not very common for bis-arene complexes. However, this double lithiation or lithiation in presence of TMEDA provides route for putting different kind of substituents on the benzene ring, and examples of 3 different reactions are shown over here. So, in one for chromium, substitution leads to the asymmetry on the ring. For vanadium, like ANSA type complex of germanium dimethyl, or dinuclear vanadium molybdenum complex of that one with substitution on the ring can be achieved, as is shown over here. So, the addition of the nucleophiles, that is an interesting reactions which sort of lead to the addition on the ring of nucleophiles, cationic bis arene metal complexes readily react with nucleophiles by ring addition. So, this is illustrated by this nice example of trimethyl 2,4,6 trimethyl benzene this is a dicationic complex, dicationic 18 electron. So, 6 plus 6 12, 12 plus 8 20, 20 plus 2 gives you 18 valence electron compound that when reacts with nucleophile like R minus, the nucleophile does not attack the metal center, but instead attacks the ring, and the ring loses its aromaticity. Iron Fe, and the other ring still remains intact, and overall this becomes a monocationic complex which can react with a second nucleophile to give this neutral compound and So, there we see the nucleophile attacking both of the rings, with the first ring getting attacked, and second the ring does not regain its aromaticity, and just the cationic complex by addition of the nucleophiles, just two of them becomes a neutral one. Similar addition has also been observed on the ruthenium complex as well, as is shown over here. Two plus with sodium borohydride gives this as the major product 75% plus the expected addition that is the minor product on so the difference is that in this case the nucleophile adds on the two different rings, but in the ruthenium this homoannular secondary addition, both the nucleophiles add on the same ring. So, in this case homoannular secondary addition is more predominant, and the reason given for this homoannular secondary addition in case of ruthenium is just that the thermodynamics favors. So, here we had seen nice addition of nucleophiles, where the nucleophile leads to the addition on the ring for cationic biserine complexes. In case of iron, what we see is that the nucleophile going on to two different rings, giving the neutral compounds, whereas in case of ruthenium what is seen that this nucleophile both of the nucleophile attacking the same benzene ring. So, homonuclear secondary addition is predominant as and giving like to the product corresponding product in 75 percentile, as opposed to the nucleophile attacking each of the two rings separately, and that is only a minor product in case of the ruthenium, and the explanation given is just the thermodynamics governs the control of these two different type of reactivity observed. Okay. So, the next after addition of nucleophiles, the another interesting reaction is addition of radicals. Now, this addition of radical leads to formation of paramagnetic compounds. Bis benzene, chromium, captures radical to form paramagnetic compound, and this is illustrated as shown over here. Bis-benzene chromium reaction with R dot HR chromium and this is a radical cation which stays in equilibrium with chromium So, overall this is a radical species because the chromium is in has an overall charge of +1 and the anionic ring has a -1. So, they cancels out, as a result that this species so formed is radical in nature, and being radical in nature, this compound is EPA reactive. So, what we had seen in terms of the reactivity is that the addition of the electrophilic substitution reaction does not occur, but instead lithiation can be affected in bis-arene transition metal complexes, and lithiation can lead to various kind of substitution reaction. We had seen that other than that one can also see addition of nucleophile, which sort of results in cationic complexes giving to the attack on the ring, and the attack on the ring can be happening or can happen for on the same ring or on two different rings, and we have also seen the addition of the radicals occurring for bis-benzene chromium complexes giving to paramagnetic species, and with that we come to end of our discussion of bis-arene complexes of transition metal, and then we are going to discuss in line with of the half sandwich type complexes. Particularly, we are going to be talking about arene metal carbonyl complexes. So, these are metal with arene and carbonyl complexes, similar to the half sandwich complexes of cyclopentadienyl metal carbonyl complexes that we had spoken about. So, the next few minutes of this lecture would be dedicated towards taking up these arene metal carbonyl complexes. So, there are several examples of this. Some of them are given over here. C6H6 V CO4 plus C6H6 Mn CO3 plus C6H6 whole 3 CO3 CO2 plus C6H6 M CO3, where M can be chromium, molybdenum, tungsten. So, what we see is in like with the cyclopentadienyl transition metal carbonyl complexes, there are a whole range of corresponding benzene transition metal carbonyl complexes, and they, to the extent that they can be treated as a class of their own, and we are going to focus now on the synthesis aspects of this benzene transition metal carbonyl complexes. So, one of the common methods of preparing these complexes involve metal carbonyl and reaction of metal carbonyl and arene plus arene, and these are called carbonyl substitution reactions. And this is given as trimethylbenzene plus molybdenum hexacarbonyl 125 degree centigrade, giving arene molybdenum tricarbonyl complexes plus 3 CO. Now, this is a very simple method and kind of very intuitive as well, because the target compound is arene metal carbonyls. So, very good way would be to start with metal carbonyls with arene and by simple heat. Now, if arene, each of the arene is a 6 electron donor, and it kind of replaces 3 carbonyls in return. Now, one can synthesize chiral complexes using these compounds, and this is illustrated by this beautiful example in which the diastereomers are formed depending on the types of the arene used, and the example given over here is benzene R, OH in presence of chromium hexacarbonyl in Bu2O THF 9:1, then what one gets is this substituents C H R OH, which is the R conformation with chromium tricarbonyl plus the corresponding R H OH, the S conformation with chromium tricarbonyl, and this is the main product. And this is the byproduct, and these they can be separated, and diastereoselectivity increases when reaction carried out in under kinetic conditions. Okay. So, with this I would like to conclude today's discussion. Today we have mainly looked at the reactivity of transition metal B-serine complexes. This was in continuation with our earlier discussion on the same topic, and what we had discussed today in particular was that these compounds can undergo selective metallation, particularly dilithiation in presence of TMEDA, and the dilithiated compounds can be further transformed to other compounds depending on various reagents. We have also looked at the reactivity in terms of addition of nucleophiles, and what we had seen that nucleophilic addition indeed take place on the ring, leading to loss of reactivity in case of cationic transition metal B-serine complexes. In some cases the nucleophiles add on the different ring, leading to loss of aromaticity in both of the arene rings in both of the two rings of the B-serine transition metal complexes, and in some other cases that both of the nucleophile attacked onto the same ring where the aromaticity of the other ring remained intact. Parallel to this reaction, we have also looked at how the radicals attack these B-serine transition metal complexes, and here also the radical do attack to the ring, leading to the loss of aromaticity of the ring and resulting in these cationic complexes. So, with this we finished off with our discussion on reactivity of B-serine transition metal complexes, and then moved on to transition metal arene carbonyl complexes, which is similar to the half sandwich complexes we have discussed for the CP counterpart, and we had seen that there are very many examples of that, and we have also taken up a preparatory method for arene transition metal carbonyl complexes, and this method is quite simple, that it involves direct reaction of transition metal carbonyls with arenes at elevated temperature, resulting in transition metal arene tricarbonyl complexes. One must note that each arene is a 6 electron donor. So, the substitution leads to elimination of 3 carbonyls, and the substitution does not go further than that. So, with this I would like to draw a conclusion on today's lecture, and we are going to be discussing more on this arene transition metal carbonyl complexes, particularly with respect to their synthesis, structure and reactivity in the next class. Till then, goodbye and thank you, and I look forward to take up this topic with you in the next class. Goodbye.